Hello, welcome to the webinar. We will get started in a few more minutes. Thank you.
Hello, welcome to today's webinar by the ASQ Statistics Division. The title of our webinar today is Designing High Impact Experiments, and it's being presented by Sherry Craver. She is a consultant with Statis with over 20 years of experience teaching engineers and technical professionals how to design and implement designs of experiments. She draws on her process engineering experiences at both 3M and Frigidaire, where she implemented statistical quality tools such as statistical process control and design of experiments. And now as the Statis workshop manager, she devotes her considerable energy and experience, and along with her leadership skills, to presenting workshops on DOE, teaching others how to make breakthroughs. And with that, I will turn it over to Sherry.
Great, thank you, Jenny. Appreciate the introduction. Welcome to all of you to this webinar. Pleased to see everybody here. I previously presented this at this year's virtual World Quality Conference, and that was a great success. So I'm looking forward to talking about design of experiments with all of you guys. So what we are going to talk about today is the 4-step factorial design planning process. And I am going to run through this planning process with a case study first, and then I'll kind of recap the steps afterwards with a few more details. One of the features of it will be looking at power and how to use power to make sure that your DOE will detect the effects of interest. And I'll also talk briefly about some great options for factorial designs, maybe some newer ones that you're not as familiar with. And of course, our goal is to run experimentation that will provide meaningful results. And the more we can do planning up front, the more likely it is that our results will be good and we'll have a good analysis at the end. So just a brief recap of design of experiments, or DOE. It's a very, very systematic and kind of statistically determined series of tests where we are trying to build this relationship through a polynomial model between the controllable factors and the measurable responses. The factors have to be controllable for the purposes of the experiment. They don't have to be long-term controllable, but they at least have to be short-term controllable so you can get the experiment done well and in a consistent manner. The responses need to be measurable, and the more numeric responses you can have, the better. It's a little bit harder to do analysis with rating systems, although that's also a great thing. I've had good success with that. And it's a little bit harder yet to do analysis with pass-fail or binomial data. So the more continuous numeric responses you have, the easier the analysis is going to end up being. We want to try to figure out this cause and effect relationship beyond the noise that's in every process. And some of us have more noise than others. I'm teaching a class right now and I have a biologist in there, and he says, how do I account for all of the noise that I have? And, well, that's where the power comes into play. We can use power to help size the design well based on the information that you have going in. So we'll talk more about that. Design of experiments should be considered an iterative learning process. We start with our conjectures. We start with everything we know about the process and what our goal is for the experiment. When I started teaching this 25 years ago, people used to be afraid that computers would take over their jobs and do everything for them and they wouldn't be needed anymore. And so we spent a lot of time in class kind of teaching people how to use the computers, how to use them for data analysis. But it all came back to the fundamental that a computer cannot replace the human understanding of your system and your process. You have to bring that to the table. You have to have a little bit of subject matter knowledge to just get started. And so we take all that basic knowledge and then ultimately we decide on a good design to use. And from there we go off and run our experiments. And of course, running the experiments is the easy part, right? Because nothing ever goes wrong. It all goes as planned. It works out just perfectly in the textbooks. No, not in the real world. In the real world, we know that we might have some missing data. We might have some points that don't run as well as we had thought. We might have somebody who misreads the run chart, and generally, problems can happen. So we have to analyze what we have. We have to analyze to the best of our ability and get at least enough information out of here that we can make good business decisions. Because we often have problems, we have to back up to the design portion and make sure that we're choosing a good, robust design, a design that will hold up to a few missing runs, a few missing data points that mess it up. So we don't want to run just the bare minimum. We want to have a little bit of robustness built in so that we can then get that decent analysis out. From this, we're then going to have new knowledge and new questions, because I've never run an experiment where I didn't end up with a bunch of questions. And so from here, we can then think, do we want to run another experiment? And we certainly can then do another design, answering new questions and get some new analysis and et cetera. A typical experimental process, I usually figure, has about 3 cycles. The first cycle just asking some basic questions. Do these factors have an effect on the responses? And then the second design, maybe digging more into the interactions or even quadratic effects if you want those. And then the third portion may or may not be a designed experiment. It might just be some confirmation runs to wrap up the whole thing and make sure that we're getting solid information out of it. So we do want to think of DOE as an iterative cycle and not just plan to get all the information at once. You'll have more success if you iterate a little bit. All right, so today we're going to be talking about this 4-step planning process. And specifically, I'll be talking about factorial designs in this planning process. So here are the 4 steps, just briefly. And as I said, then we'll look at a case study, and then we'll come back and look at these in a little more detail. So the first thing, this is all good engineering topics. Always have to say, write down your objective. What is the goal of your experiment? I get many people sending me a question, hey, I have 4 or 5 factors I want to study. Which design should I do? Well, I don't know. I need to say, what is your objective? Are you trying to find out if these factors have an effect? Are you trying to fully characterize the interactions? Are you trying to get curvature? You know, you have to spell that out a little bit. So we write down our objective. Then we focus on the responses. So objective first, then responses second. What do you know about the responses? We want to detail the responses in terms of a signal to noise ratio. So we'll be looking at that. Then step 3 is then to define the factors that you think will influence those responses and what ranges you want to test over. And then finally, given all of that information, we get to choose a design and make sure that the design is going to hold up well. So we have a few evaluation things that we can do when we look at designs. All right, so we're going to do a little food case study. Food is always good. Everybody likes food. This is a favorite of mine in the winter time, especially good old pot pies. And this is a manufacturer of pot pies who is mass producing these and then freezing them, and then they go into the grocery store freezer, and you pull them out and pop them into your oven and finish baking them. So they want to get a good crust. The dough crust is the objective, to really get a good consistent crust. While they are manufacturing this and forming this crust, they want to keep the dough temperature at 70 degrees. They have found out that even a few degrees change in the temperature can actually degrade the bottom crust. So keeping that temperature consistent is really critical. They have found out that there are some possible things that might affect this consistency of dough temperature. And so they want to figure out the influence of the dough batch size, how much of the dough are they making at once, whether they can rework dough scrap back into the process. I mean, because what manufacturer doesn't want to keep recycling some stuff and keep their overall waste to a minimum? And then the amount of ice that's used. They're using ice to help cool the dough temperature and keep it so it doesn't warm up. So we're looking at these 3 things. All right, so number 1 in our 4-step process is to write down our objective. What are we trying to do? So the objective is to find or to determine the effects of the dough batch size, the scrap quantity, and the ice quantity on dough temperature. Okay, pretty straightforward. Number 2 is the trickier part. Now we're going to start thinking about the responses, the measured response. And here, as stated in the objective, they are focusing on the temperature, the dough temperature. So they're closely monitoring the temperature, and they need to define the change, the minimum change in this dough temperature that's important to detect, meaning the software would say, hey, this amount of change in the dough temperature is statistically significant and you need to take notice of this. So the team decides that a difference of 3 degrees Fahrenheit in dough temperature is of interest. So our delta Y, our signal, is going to be 3 degrees. This is entirely a business decision. It is not a statistical decision whatsoever. It's what is important for the business. Okay, so given that, then the next part is a statistical determination. We have to estimate the standard deviation for the response. So we can look back at historical data for dough temperature, and we look at a sample size that you have to determine. You have to take, a sample that is a representative sample, one that's going to represent the normal process variation, and pop all that into something like Excel and get it to calculate the standard deviation for you, which they do, and it's 2.2 degrees F. Okay, so now we put those two things together, the signal and the noise, and that gives us a ratio of 1.36. This is going to help us estimate the power of the design that we choose to see how well the likelihood that the design is going to detect this change in temperature given the standard deviation of temperature. So we'll get to that. Okay, putting that on hold for a minute, we're going to return to our factors. We have to put our input factors in. So batch size, here's the 2 batch sizes, 590 pounds to 750 pounds. Okay, now I have no idea why they did 590 here versus 600. And perhaps that was just, what it turned out to be in the manufacturing process. I don't know. The scrap quantity and ice quantity, you'll notice that those are written as basically absent with 0 pounds, so none of it, or present, 340 pounds of scrap or 40 pounds of ice. So that is certainly one way of doing it. They didn't do like a low value and a high value. It was really nothing or something. And we can fit a model to those numbers. All right, so we select a design, and we're going to start with a full 2 to the 3rd 2-level factorial design. We have 3 factors, we have 2 levels, so this is going to be 8 runs. Just a classic little 8-run design. They are so nice. Since it's a full factorial design, we don't have to worry about aliasing. Aliasing is not an issue because we're running all possible combinations. But if you were doing a fractional factorial design, then you would always want to look at aliasing. We would want to look through all the factor combinations and make sure that they are safe and reasonable, that we are likely to produce meaningful information, that we're not going to have any problems with them. And so we assume that the team knows from some subject matter experience that everything in these runs is going to work and is going to give us meaningful information. And the other part of evaluation would be looking at power. We will talk a little bit more about that coming up. All right, so we would use a software package, and just a disclaimer, I work for StatEase, so Design Expert is my favorite package, but there are many other software packages who could also do this. We will put in our factor names and units and the levels. And from that information, we would run a power test. And in Design Expert, it's just one of the screens that is put right in front of you. Given the change in temperature that we're trying to detect, the 3-degree change, and the noise of 2.2 standard deviation, that gives us a signal to noise ratio of 1.36. And that, through some magic of calculus, which is definitely not something that you want to do by hand, but there are plenty of power calculators out there. The power to detect the main effects is about 31.7%. Now, we would run an 8-run design with this signal to noise, and the power is 31%. That means that if you did this 8-run design, your likelihood of finding a 3-degree change is only 30%. That's terrible. That's awful. I would not want to run an experiment where I only had a 30% chance of success. No, we want power to be at least 80%. That's just a rough guideline. Somewhere in that 75 to 80% likelihood is a good guideline, so that you have enough probability that you're going to find the significant effects, that it works. So let's just talk a little bit more about power, since that's one of the things that we came here for. Okay, I have 2 ways of explaining power. The first way is the statistical way. And then the second way is my golf analogy. So hang on, and we'll get to the golfing bit here in just a minute. But let's look at this from our truth table. Now, the truth table has 2 parts. We have the truth, which comes from the data, and we could either have an effect, yes or no. And then when we do the data analysis, the ANOVA is going to recommend that we either retain the null hypothesis, which means there's no effect, or reject the null hypothesis, which means there is an effect. Okay, so our favorite place to be is down in this lower right-hand corner, where the ANOVA is saying, hey, reject the null hypothesis, you have significant effects. And the truth is, yes, we have significant effects. That's great. We love to be there. That gives us pride in our work, that yay, we did a design of experiment and we found some significant factor effects. Sometimes the ANOVA tells us, hey, reject the null hypothesis. There's something here, and yet the p-value is maybe just right at 0.05, or maybe it's a little bit smaller, 0.03 or something like that. But the truth, the real truth in the system is that there is not an effect. This is a false alarm, and this is what we're always trying to protect ourselves against. The p-value is the indication of how likely it is that we're going to have this false alarm, and so we pay a lot of attention to this. And it's the type 1 error or alpha rate, alpha error. Okay. Beyond that, over on the other side of the camp here, we're also in a good area where when the ANOVA says retain the null hypothesis, nope, nothing here. And the truth is, there is nothing there. That's also a good result. And we look for that kind of result when we're doing ruggedness testing or robustness testing, when we're actually running an experiment to prove that there are no effects. And you think, well, when would I ever do that? I have clients doing that all the time, especially now in the pharmaceutical industry, where they have to validate their manufacturing processes and show to the FDA that they have robust manufacturing processes, that even with small variations in the manufacturing process, we can still get reliable results. The quality stays the same, stays good, even if there's small variations. So that is also a good result. But here's where we get into trouble. Sometimes the ANOVA says retain the null hypothesis. There's nothing here. And yet the truth is there really is something significant in the system. That is a failure to detect. That's a type 2 error, your beta risk. And that is one that we forget to look at. But that's really the function here. We want to make sure that the design that we're running has the power to detect the effect that we're looking for. And so the definition of power is that it is 1 minus beta. That's this number here, 1 minus beta. Yeah, we multiply it times 100 to get it into a percent. So power is the likelihood of finding an active effect of size delta relative to the noise. And we want power to be high, generally at least 80%. And so this is why we went to the trouble of defining the response information. What's the minimum change in that dough temperature that we want to find? We said that was 3 degrees. And what's the standard deviation of dough temperature over some sample? So that was 2.2. So we get that signal to noise ratio, we throw it into a power calculator, and we want the power to be able to find that to be at least 80%. Okay, so that's all the statistics and all that statistics lingo. Let's talk golf. So here's my little golfer up here. The golf ball represents the effect that you're trying to detect. And the grass represents the noise in the system. And so we have some probability of finding the golf ball, which increases as the ratio of our signal to noise increases. Okay, so let's look at this backwards. Let's look at this big signal to noise ratio. So, you know, I can golf, not well at all, but at least I know what golf is. If I were to go out there and somehow magically hit that ball and it lands right in the middle of the fairway, then I can see it, right? From where I'm standing, I can see the golf ball. It's sitting up high above the grass. And it's just easy to find, it's easy to detect. My p-value of finding that golf ball would be very high. If I try again, and this time my golf ball lands closer to the edge, you know, they let the grass grow a little bit longer on the edge, and maybe I have to walk and get a little bit closer to finding that golf ball. Just, you know, I can still find it, but it gets harder. Okay, then reality sinks in. You know, this is where my golf balls really go, which is in the rough, in that big, deep grass. Definitely can't see it from the tee. Now, how are we going to find the golf ball that's hiding in the grass? So we have a low signal to noise ratio. Well, we have to figure out how we can manipulate this system. We can choose the size of the ball that we're looking for. That's a business decision. And so I could play with, instead of a golf ball, maybe I'm using a softball or a wiffle ball or something like that. And a bigger ball is going to give me a bigger signal to noise ratio. So this is something that's going to increase my power. Now, the other thing I can do is I could get the lawnmower out. I could mow down that grass. And if I mow down the grass, then I'm going to change my signal to noise ratio again and increase the likelihood of finding my effect. Now, ways of mowing down the grass are things like blocking. If you've heard of blocking in design of experiments, it's a classic lawnmower effect, and reduce the grass, the noise in the system. The last way of finding my golf ball is actually, you gotta be a little bit more creative with the analogy here. It's ask my buddies to help me. I'm probably golfing with 3 other people. We probably have a foursome because that's a lot more fun. And if I ask everybody to help me look for the ball, help me search the ball, that's going to increase my probability of finding the ball, right? Yeah. So this is analogous to adding more runs to your system. If you have more runs, that's like more people walking around looking for the golf ball, and we can find it more frequently. We have a higher probability of finding it. So those are the things that we can affect. We can affect the size of the difference that we're looking for, the change in the response. We can change the noise in the system, if that's at all possible, reduce the noise in the system to get higher power, and increase the number of runs in the experiment to get higher power. So all of those things are things that you should be thinking about when you're running an experiment or planning the experiment, really. Okay, so for this case study, what we're going to do is we're going to add 2 more replicates. That's going to give us a total of 24 runs. We had 8 runs to begin with. 2 more replicates will give us 24 runs. When we do that and we check the power now, so we haven't changed our signal, we haven't changed our noise, we've just increased the number of runs. Now our power is up to 88 to 89%. So this is good. Now I feel like I have a chance to be successful in running this experiment. Yay. All right, so I'm going to show you a few screenshots to just kind of wrap up this case study, and then we will get back and review power and some design options for a few more minutes. All right, so a 2-level factorial analysis is generally best done visually using a half normal plot of effects. You can see the effects that are not normally distributed, the ones that jump off the line. So here we have the amount of ice, the amount of scrap, and an interaction between those. And also shown on a Pareto chart, which has a couple of t-values on here. We have a basic t-value, and then we have a multiple comparison t-value that's a little bit more conservative. So these 3 effects are much, much larger than the other 4 possible effects. So we're gonna put those 3 effects into the model and leave the other 4 to be pooled together into the residual. So we get our analysis of variance, which looks something like this. The model is statistically significant with a p-value of 0.0026. Each of our individual effects terms is statistically significant. And because we had replicates now, we have another statistic that we can look at, and that is called your lack of fit statistic. And lack of fit is not significant. So that's a good thing. It means the model fits. So when lack of fit is not significant, that means the model fits. Okay, so we are sitting good here with a significant model and insignificant lack of fit. You always want to back up your looking at your ANOVA with checking the diagnostics. Diagnostics are going to tell you if you have outliers, if you have non-normality of the residuals, if you break the rule of constant variance, or if you have any trends going on over time. So here's our normal plot of residuals, a nice straight line there. The residuals versus predicted, we're looking for constant variance. So the range of the residuals from the left side of the graph to the right side of the graph should be about the same up and down range, which it is. We're not going to worry about this blank in the middle. Doesn't matter at all. It's just how the response data happen to fall. Then there's a residuals versus run chart. So I would make sure that there's no trends. It's a nice random scatter. And I see that there's no outliers. So nothing outside the red lines on either of these two graphs. So all the data is being modeled well. And there's a box-Cox plot for transformations. We don't have any recommended transformations here. This is a very, very low, shallow plot. If we needed a transformation, there would be a legend on here that would say it would recommend whatever it was needed, a log or a square root or something like that. But all of the diagnostics look really well, really good in this graph. So we can wrap this up finally by looking at an interaction plot. And this interaction plot is the interaction between the amount of ice and the amount of scrap. So the x-axis has the scrap quantity going from none to 340. And the ice quantity has the black line is actually the no ice. It says low ice, but it's really no ice. And then the red line is the higher amount of ice. And we were trying to achieve a consistent 70-degree dough temperature. So it turns out if we keep the ice low, then the scrap quantity can actually be from none to its high amount. And there is, it looks like we'll keep the dough temperature consistent. Now, I will just throw in here that we did not do center points in here, and center points are certainly something I would recommend so that we could have checked these middle conditions and confirmed that this is a linear analysis. But this is just an illustrative example so I can talk about the process, the DOE planning process. So no need to comment on the lack of center points. I would highly recommend that we do them. All right, so back to recapping our planning process. We started out by defining our opportunity and our objective. Then we started thinking about the responses, defining the smallest change that's important to detect. So let's look at that for just a minute. To define your signal, ask this question. What is the minimum change in the response that would be recognized as an important improvement? It's a business decision, not a statistical calculation. So as an example, another example, let's say we needed to improve yield and its current level was 80%. Okay, 80% yield is awesome. Every percent increase is worth $100,000 per year in profits. So get a little financial information to be included in here in your decision-making process. What amount of improvement would be valued? And we have to make a quantitative decision. So, I mean, if we could make a 10% change in yield, obviously that'd be like $1 million. That I think most companies would value that. Now, if we made a 1% change in yield, that's $100,000 per year in profits. Probably pretty good. For most companies, they would take that. How about a 0.1% change? Well, now maybe that's down where we don't care so much. So the value of the improvement is what you need to consider when you think about how much change in yield is worth the cost of doing the experiment. Because, I mean, quite frankly, if you ask any manager, how much of an increase in yield do they want to detect? Manager is going to say, well, any change in yield, any improvement in yield is going to be important. Okay, if we were trying to detect any improvement, that could be a very, very small number, and that's going to take a lot of runs. Your signal to noise ratio is going to be really, really small, and it's going to take a lot of runs to find it. So the value of that is not good. You have to think, you know, really what's the smallest change in yield that I want to spend money to find? So it's a trade-off. All right. Then, of course, you have to think about those factor ranges. You need to have ranges that are wide enough that it's going to cause a change in the response, but not too wide so that you would get immeasurable results. You know, that you can't even get a good solid measurement out of. So that is something a statistician really can't answer for you. It's a subject matter knowledge decision. You might even have to do one factor at a time studies in order to figure out a good range to put into your design of experiments. That's okay. Okay, then we finally get down to part 4, select a design. And that's what I want to spend just the last few minutes here on, just considering some design options. So criteria to consider when selecting a design. Number one, often people think, oh, number one is how many factors you want to do. No, 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 no. Number one is what is your budget, right? You know, realistically, budget is money. So how much money do you have to spend on this experiment? Then based on that number of runs, what type of information do you want to get? Do you want to get main effects? Do you want to get interactions? And this comes down to, you know, what type of design you would do. A design that's really meant for screening, or a design that's meant for characterization, meaning we get interactions and probably some center points to detect curvature. Or maybe we're doing that ruggedness testing that I talked about, where we're just trying to validate that a process works. And lastly, the power of the design. Okay, so there are different types of designs to choose. There are regular, 2-level, full and fractional factorial designs. And there are minimum run type of designs, and these come in various forms. Different software packages have different types of designs, but minimum run characterization, resolution 5 minimum run designs are good. We will talk a little bit more about these in a second. Then if we're looking for resolution 4 designs for screening, then again, there's minimum run designs. There are regular designs that are resolution 4, and there are definitive screening designs that are kind of a hybrid. There are resolution 4/RSM type of design. They have some aliasing between the quadratic terms and the interaction terms. So they're kind of a quasi resolution 4 type of design. And then Plackett-Berman designs are a resolution 3 design, which would be appropriate for that ruggedness testing. So I was trying to kind of color code some things depending on the type of information that you want. Full factorials are always going to give you all effect information, so that's always a good thing, but they get large quickly, you know, a lot of runs. So we often go with characterization, and in Design Expert we have these color-coded green designs that are going to give you the main effect information and your two-factor interactions. So really good. They're usually my go-to designs, like this 5-factor and 16-run design that's right here, green design. That's just an excellent design. Screening would probably be one of the yellow designs, the resolution 4 type of designs. Screening, a good screening design should separate the main effects from the two-factor interactions, so that you can get unbiased estimates of your main effects. Because we have shown that if there are interactions in your system, that they will bias the main effect results and can even mask them. And you can literally lose your main effects if you do a design like a resolution 3 design to find main effects in the presence of two-factor interactions. You will run into problems. You may get some correct information, but you probably will not get all correct information. So, you know, we want to set ourselves up for success with a good design. But those resolution 3 designs are great for the ruggedness testing, trying to find no effects. Okay, so for any design, we want to check aliasing. Which effects can be estimated cleanly versus which cannot. And I didn't have time in this webinar to get into aliasing, but you know, if you're not familiar with it, it's probably the #1 thing that you should seek to understand. Partial aliasing can be okay. We have a lot of great designs. Our minimum run designs have partial aliasing. Plackett-Berman designs have partial aliasing, provided that the software that you're using has analysis tools that will pull out the effects correctly. So again, you got to go back to a good software package. And even for the goal of ruggedness testing, you want to check power. Can the design detect the response change of interest relative to the noise in the process? So even if your goal is to show that there's no effects, the design needs to have the power to detect the effect. Otherwise, you're not really proving anything. And we've certainly seen plenty of write-ups with people who have definitely chosen designs that were too small to find an effect, and they think that they're proving that the process is rugged, and they're really not, because the design wasn't capable in the first place. So check power, check aliasing. All right, so this is the 4-step factorial design planning process. Again, define the objective, state that objective in terms of your responses, and you might have a lot of responses, so figure out which responses are kind of your worst case signal to noise ratio and size based on those, because if you get your worst case responses, then everything else will be good. Figure out what factors you want to study, how many. Figure out those ranges that you want to test. Set those ranges far enough apart to induce a change in the response. You know, so be bold in setting them, but don't overkill it. You still have to get measurable results. And finally, then choose a few designs. Check a couple of different designs and evaluate them and figure out which one is going to best meet your needs. There's no right answer. There's several things that can work. All right, so ultimately your DOE is going to provide meaningful results if you follow all of these rules. With that wraps up this presentation. We can open it up for questions, and if you want to email me, my email is on the screen here, sherry@staties.com.
Sherry, are you able to see the questions, or do you want me to read them to you?
Let me open up the panel here. I am not able to see them, so if you could read them, that would be great.
There's a question about experimenting on an unstable process, if it's acceptable to do that, if it's out of control, or do you need to wait until it's stable?
Yeah, that's a great question. The response has to be stable enough that you think it's going to be fairly predictable. You know, that you can, that if you're going to use it for predictions, that you can make some predictions out of it. Now, if you're just trying to detect some effects, then maybe it doesn't have to be very stable for the moment, but just, you know, I say temporarily stable. And I've certainly done that with brand new processes where I really don't even know that they're stable yet. But, you know, you interpret appropriately. If you know it's not stable, then, you know, you take your results with a grain of salt.
There's a couple of questions about the software that you use.
Sure. I use a Design Expert DOE software. And if you go to statease.com, you can get a 30-day trial there. And if you email me, sherry@statease.com, I'd be happy to answer those questions individually. I'm also happy, I see actually a couple of people are sending me LinkedIn connections. I'm active on LinkedIn. I'd be happy to connect with anybody who finds me there.
There's a couple questions about how important the normality assumption is to the power calculation, or just to DOE in general.
So normality is somewhat important, but it's not as important as the assumption of constant variance. So I worry more about constant variance than I do about normality. But really, I take all of those diagnostics as a group, and I don't put too much emphasis on any one diagnostic. If as a whole they're looking okay, then, you know, I would certainly go ahead. And again, if the worse they look, then the more grains of salt I'm putting into my reliance on the final analysis.
There's also a question about the cost of increasing the replicates to increase the power. Sometimes that could be very costly. Are there other considerations on how to increase the power?
Yeah, well, you have the three legs that power stands on, which is the size of the effect. So if you can increase the size of the effect, that increases your signal to noise ratio. If you can reduce the noise, so figure out any way to cut back the noise in the system a little bit. I know that's the hard one, but anything that you can think of to reduce the noise will help increase that signal to noise ratio, and then to balance out the runs. Sometimes you can replicate at the point at which you have the most amount of variation. Like there's, you know, we didn't get into like components of variation but variation comes from the process. It comes from the sample to sample. It comes from the test measurement itself. And so if you replicate at, say the test measurement and put in an average, then an average of some repeated measurements, then that will actually reduce the noise in the system and make things easier to detect.
There was a question on whether the seminar is being recorded for viewing later, and I can answer that. It is being recorded. You'll be able to access the link through the ASQ website. And there will be a attendance confirmation emailed to all the attendees after the fact. That was a question. And then there's a question on what do you do if you don't have a good estimate of the standard deviation of the response?
Great question. You take a swag at it. Swag, S-W-A-G, write it down. It's scientific wild ass guess, but emphasis on the scientific there. So you estimate it. The ratio of signal to noise is more important than the numbers themselves. So like our software always defaults to a 2-to-1 signal to noise ratio. It's a pretty common signal to noise ratio. If you have another product or response that's similar, you can use that. And so just a reasonable guess.
Could you speak more on the benefit of blocking designs?
Well, that's a whole nother topic in itself, but I'll give you a quick thing. Blocking is a tool that reduces the noise that's coming from a variable that's changing during the DOE that you are not interested in studying. So I often use day-to-day differences. If you have to run your experiment over 2 days, then Monday is probably a little bit different from Tuesday. So I would block on the days. I'm not studying day-to-day difference. I just want to remove that source of noise from the ANOVA before I calculate any of my factor effects. So yeah, blocking is a great tool. It does get abused by people who block on a factor that they're actually trying to study. That will cause you permanent and irreparable harm to the analysis. So don't do that, but block on things that you're not studying.
And do you have a recommendation for the best DOE method to find the optimal input parameters to achieve optimal responses in one or more outputs?
No, that is too general of a question. Yeah, there's lots of great designs, but it would depend on the situation, because there's great designs out there, many of them, but it depends on how many runs you have, how many factors you have, all those things.
Great. That was a really good webinar, and thanks for answering all those questions. I think that's the majority of them. But do you have any final comments before we end for the day?
No, thank you. I appreciate the opportunity to give this webinar and enjoyed it. And so I hope to hear from some of you later on. Thank you very much.
Thanks everyone for attending. Bye for now.